Okay, so we are going to use Newton's method to minimize this cross entropy, and this would be a good time to go check out the video on Newton's method. Assuming you have done so, what we need to do now is to compute the gradient and the Hessian matrix of this cost function with respect to W, right? And of course, gradient, Hessian, all of them are linear operations. So you can just focus on one term, one of these n terms, and figure it out, and then put the summation in, right? So that's what we are gonna do now. Okay, so let's look at the gradient of one of these terms, right? And we are going to be having to apply chain rule a lot here. So let's look at the gradient of this. Yi, of course, does not depend on W. These are the labels that are given to you. So let's take the gradient of that term above. So Yi just comes out. Chain rule means when I differentiate the log with respect to Yi hat, I'll get 1 over Yi hat. And then I have the gradient of Yi hat with respect to W. That's the first term. Then 1 minus Yi stays unchanged because it's the labels that are given to you. Log of 1 minus Y hat is 1 over 1 minus Yi hat. And then I differentiate 1 minus Yi hat with respect to Yi hat. I'll get a minus 1 there. So that's this guy. And then again I have the gradient of Yi hat. So it's clear that I need to compute the gradient of Yi hat here. So let's take a break and do that. So now what's Yi hat? Yi hat is the logistic function operating on W transpose phi. Right. So again, I'll have to apply the chain rule here. So before doing that, let me just find the derivative of the logistic function. So let me look at sigma of z and its derivative. And so that's d by dz. Let's write down the thing for the logistic function. It's 1 plus e to the minus z in the denominator and 1 in the numerator. And so when I differentiate that, I'll get minus 1 over 1 plus e to the minus z squared when I differentiate with respect to 1 plus e to the minus z. And then when I differentiate 1 plus e to the minus z with respect to z, I'll get minus e to the z, right? That's what I get. And so that I can write as 1 over 1 plus e to the minus z and e to the minus z over 1 plus e to the minus z. Why am I writing it like this? It's because this guy is just a logistic function and that guy is 1 minus the logistic function. So the derivative of the logistic function has a very nice form of p times 1 minus p. Each of these are probabilities between 0 and 1, right? So now I'm going to go back to, let me change pen color. I'm going to go back to this guy and compute its gradient, right? So the gradient of Yi hat is the gradient of the sigma of W transpose phi, right? And again, I'm going to apply chain rule. So I'm going to differentiate sigma with respect to its argument. And so then I'll get sigma of W transpose phi times 1 minus sigma of W transpose phi. That's just this business out here, applying it there. And then, so that's the derivative with respect to W transpose phi. And then, of course, I have to take the gradient times the gradient of W transpose phi, right? And I'm going to change the pen color back to blue to write down the final answer, which is basically, oh, by the way, remember that sigma of W transpose phi is exactly Yi hat. So it's Yi hat times 1 minus yi hat. And then the gradient of this is, just you can check very quickly, is just phi itself, right? So what we have is yi hat is that quantity. And now I can go back to what I had before, where I was looking at when I was looking at del W. What was it? Let's go back and look at it. This guy, right? Yi times log of yi hat plus 1 minus yi times log of 1 minus yi hat. We'd already figured this out. It was yi over yi hat minus 1 minus yi over 1 minus yi hat. I had that times del W of yi hat. Let's go back and check that that's actually true. Yes, that's exactly what we had here. Let me change pen color to highlight it. It's this guy, right? That's what I had. So I'm going back there to and plugging things in and simplifying now. If you look at this term here, what is it? Yi times 1 minus yi hat above minus yi hat 1 minus yi there divided by yi hat 1 minus yi hat. And if I look at this, I have yi minus yi hat minus yi hat plus yi hat, so that cross term goes away. So this is going to be equal to yi minus yi hat divided by yi hat times 1 minus yi hat. Gets a bit messy, but now you can see, again I'm going to change pen colors here, that this term below in the denominator, when you plug this expression in here, will cancel out the yi hat times 1 minus yi hat term in the numerator, right? So now I have a very nice simple expression that del W yi hat log yi hat plus 1 minus yi log 1 minus yi hat. I'm sorry having to write this expression so often. Mainly sorry for myself. It's yi minus yi hat times phi. So that's what we have there. And now remember that we have a negative sign out there and a summation out there. So when we put it all together, what we have, and let me change pen colors to emphasize this, that del W of E of W is summation I equals 1 to n. When I put the minus sign back in, I'll have yi hat minus yi times phi. Phi's are these d cross 1 column vectors. And so now I can actually collect these things into vectors and say this is actually equal to phi times y hat minus y. Right, so what is phi? Phi has as column vectors phi1 down to pn. So basically d cross n matrix, and y hat minus y is basically y1 hat minus y1 down to yn hat minus yn. This is an n cross 1 matrix. So this is what you would expect it to be. This guy, I'm going to change it back to emphasize. This is a d cross 1 gradient vector, right? So let's recap. what we showed was that these estimated probabilities for the labels vary with W in this fashion. So their sensitivity is based on this, based on these probabilities that I'm spitting out yi hats that I've computed. Yi hat, of course, is sigma of W transpose phi. So I have that, and then I have the gradient of E of W compactly written as this phi matrix, and then times the y hat minus y vector, right? In order to apply Newton's method, I also need the Hessian. And we have seen that the Hessian is compactly written as this. A lot of people, as I said, write it as gradient square, but really, in order to get the dimensions to work out right, it's more accurately written as gradient transpose operating on the function. So the gradient gives you a d cross 1 thing. It's a d cross 1 business, and gradient transpose is a 1 cross d, and so that's how it works out, right? And so I don't think I need to go through the whole thing again, but what I get when I do this is I'm going to operate this on I equals 1 to n yi hat minus yi phi transpose. This is my gradient transpose of E of W, and so that is of course just summation I equals 1 to n the gradient of yi hat times phi transpose, right? And we already know what the gradient of yi hat is. It's summation I equals 1 to n yi hat times 1 minus yi hat times phi. I apologize, I'm not sure why I put the phi hat here. It was just phi, of course. Phi oh, sorry, I meant transpose there. So, okay, that's what happened. So I was putting hat instead of transpose. So I have del W yi hat is this guy, and then I have the phi transpose term there. So basically, each of these guys, phi is d cross 1, this is 1 cross d. Each of these guys is giving me a d cross d outer product matrix, and I'm weighing them differently depending on how far yi hat is away from 0 and 1, right? So basically, the closer yi hat is to 0 or 1, the closer this is to 0, and the closer this is to half, that's sort of the maximum point. And when this is close to half and you have no certainty about it, then this goes to 1/4. And again, this thing can be written again in matrix form as, remember the matrix phi, and then I'll put an R here and phi transpose, where basically we are going to be weighing these different phi transpose terms differently. So this R is this diagonal matrix of these yi hats 1 minus yi hats guys, right? So that's the Hessian matrix. So let me put a little box around that. It's important, right? And now I can apply Newton's method, the usual Newton's method, where the kth or the k plus 1th iterate is the kth iterate minus the inverse of the Hessian at that point, and then the gradient evaluated at the kth iterate, right? And in our case, this becomes just when I just plug these things in, it's this minus phi r phi transpose inverse, and then the gradient itself is phi times y hat minus y. And this has a least squares type field to it, but I have this reweighting that's always happening. Let me put a red thing here. Reweighting by what kind of y hats I'm spitting out. I'm going to call it reweighting. And it can be put in terms of each wk plus 1 can be thought of as a solution to a least squares problem whose parameters or weightings depend on the solution at the previous stage. But and hence this is also called iteratively weighted least squares. But I am not going to make a big deal out of it because it doesn't really bias anything. So there we have it, the Newton update method for logistic regression. If things are going well, you converge pretty quickly, and you can basically process the entire batch of data at one time. The phi matrix contains the feature vectors for all the data points. Or if it gets too unwieldy, one can actually look at batches and do it. In the homework that we have, the size of the training data typically that you need is going to be small enough that you can do it probably all in one batch, but you should find out for yourself. The one other thing that is actually super important is the issue of regularization. So let me mention that quickly. So basically, if I don't regularize, and I'm going to talk about regularization means, I could basically be trying to get really good results for the training data points. What does really good result mean? It means that my y hats are going to be really close to the labels that you give me. The labels that you give me are 0 and 1. So y hat close to 0 or 1 often corresponds to y hat I overfitting the training data, right? When does this happen? When W transpose phi I, when this is large, right? Because yi hat is sigma of W transpose phi I. It tends to 0 as W transpose phi I goes to minus infinity, and it tends to 1 as W transpose phi I goes to plus infinity, right? So basically, we don't want W transpose phi I to get too large. So want W transpose phi I not to get too large, right? That's basically what we want. And how do we prevent that? Well, we just stop W from getting too large, right? We have the Cauchy-Schwarz inequality that says that if I take a inner product between two vectors, the size of that inner product is bounded by the Euclidean norms, the so-called L2 norms of those two vectors. So one way of keeping these W transpose phi I's under control is to just constrain the L2 norm of that, right? Constrain on, and typically we put a constraint on the square of the L2 norm because it's a much nicer thing to work with. It's just W transpose W. That's what the L2 norm is. So instead of minimizing the original cost function, we can minimize the regularized cost function, which is the original cost function plus some term that penalizes the L2 norm from getting too big, and where this term lambda is bigger than or equal to 0. It has to be strictly bigger than 0 to offer some non-trivial regularization, and we'll consider that to be a hyperparameter that we play with. Hyperparameter, right, that we play with. So that's the essence of regularization, and the nice thing about choosing this quadratic W transpose W term is that both the gradient and the Hessian are really easy to compute. The change in the gradient, so del W corresponding to that term is just lambda W, and the Hessian corresponding to that term is just lambda times I, and you can check that out in the notes, the detailed computations, but it's really quite simple. And the Newton iteration is modified appropriately. Again, that's specified in the notes. I also state in the notes that you can actually constrain different components of W differently by choosing by choosing different weights for the different components, and you can do it by using some sort of diagonal matrix in there. I don't want to go through that here. You can just look it up in the notes as you need to. And the final step I wanted to just mention is what happens after you train. So your training has given you W opt, and a new data point comes in, X star comes in, and you want to predict a label for that, right? So according to your model, the LLR Z star, which is the log of the probability that Y equals 1 given X star, and the probability that Y equals 0 given X star in the denominator, is equal to this W opt transpose that you've learned from your training times phi of X star, right? And so, remember that if Z star is positive, then the probability of Y equals 1 is bigger, and if Z star is negative, then probability of Y equals 0 is bigger, right? So basically, I can do a hard decision directly by saying, so hard decision is simple. Basically, Z star bigger than less than 0, and I'll say 1 or 0 based on that. Soft decision is just very simple. The logistic function sigma of Z star is the probability that Y equals 1 given X star. This is my soft decision. So that's the inference stage, right? Based on your model, you can make that inference. How good it is, of course, depends on how good the model is. That's it.